Welcome to our webinar today. My name is Shari Kraber, and I will be talking today about how to reduce your experimental runs using fractional factorial designs. You'll notice that everybody is on mute. If we have time, I will take questions at the end, but I would welcome you to type in questions into the questions box, and I will certainly try to answer those at the end. If I don't have time, I will definitely reply via email. This presentation is being recorded and will be posted on our webinars page and on our Statistics Made Easy by StatEase YouTube channel. If you haven't been to our YouTube channel recently, we have really updated it, added all of the webinars that we've been giving over the last couple of years during COVID. We have increased our webinars dramatically, and so they are all on our YouTube site. In particular, look for the corner called Academic Corner Resources for Researchers and Students, and this is for everybody. This is kind of our basic getting started webinars, and there's a lot of awesome resources there. Today we have a few main topics. I'm going to start by just kind of reviewing how to plan a DOE based on the type of information that you want to get. Then we'll be expanding on that, say, okay, now based on this information, how do you create a fractional factorial designs? This is kind of under the covers. You don't have to actually do these things because the software is going to do it for you. But this will also cover the concept of aliasing, why we care about aliasing, how to read those aliasing patterns. Those will all be done in basic regular fractional factorial designs. Then I'm going to move into demonstrating some minimum run designs that have partial aliasing in them, and we'll wrap it up with a recap of our guide to choosing these small run designs. So, planning our experiment. As you start planning your experiment, you want to start with defining the responses that you're going to measure. This is really important. People sometimes think about the responses afterwards. They're busy thinking about the factors first. But you are trying to change your system so that your outputs can be improved. So measuring those outputs is really super, super important to make sure you've spent the time to ensure that your measurement system is going to produce accurate and ideally numeric results. Try to avoid pass-fail measurements if at all possible. And an alternative to pass-fail would be using a rating system. That's kind of a little bit of an improvement. But ideally, simple numerical results are best for your responses. Then you can think about what factors you want to study, what is likely to influence the responses, and what factor range should be studied. Remembering that you want your factor range to be set far enough apart that you're going to cause a change in the response, and yet not so far apart that you can't measure the response. It goes outside the range of operability. So, we can't really help you choose what range to do, but just remember to set it far enough apart that you actually induce a change in the response. That's super important. Step 3 is what we are going to be focusing on today, choosing a design that provides the information that you need. We're thinking about the strategy of experimentation at this stage. So are you doing things like screening, characterization, optimization, or Another topic would be ruggedness testing, or kind of showing the robustness of your design space. So we will talk about those in this little segment. I also want to point out that choosing the design also depends on your budget. So make sure that you plan your budget in advance so that you can afford to go back to the system to run model verification points to confirm your analysis results. This is absolutely the key last step of experimentation, is to actually verify the results of the designed experiment. Okay, so you may have seen this before, our strategy of experimentation. And to expand on this, you can go into our YouTube channel and look for this webinar called Know the Score for Multi-Factor Strategy of Experimentation. SCORE stands for screening, characterization, optimization, and the R in this actually stands for the ruggedness testing, which I will talk about. So in screening design, the concept is to detect main effects. We're going to talk about this. And so that's just your basic linear effects. Then you move into characterization designs, where we can define the interactions in the system. And optimization is generally considered for response surface designs, where you're making precise predictions. We are not going to be talking about that segment today, because we're going to be focused on fractional factorials, which are used in the first two portions of this flowchart. Okay, so we always have to think about what kind of information we want the design to give us. People are always sending me a little request, say, hey, Shari, I have 6 factors that I want to study. What design should I do? And I can't answer that question without more information. What type of information do you want to get, and what is your budget? So a screening design will reveal the significant main effects in the system. We might call those the linear effects in the system. Now, at Staties, we do assume that interactions exist in the system, because, quite frankly, today's processes are fairly complex. And it is pretty likely that there are going to be interactions between factors. And so based on that assumption, then it's really important to use a design that keeps main effect information unbiased from two-factor interaction effects. So we'll talk about this as we talk about aliasing and the choice of design. But this is a really key assumption. And I've certainly heard people say, well, I just want to do screening design. I don't care about interactions. It's not whether or not you care about interactions. It is whether interactions truly exist in your system or not. If there's the possibility that interactions are there, even if you don't care about finding them, if they might be there, then you have to make sure that you use a design that keeps that main effect information unbiased from two-factor interactions. All right, characterization, that word is used when we want to identify both main effects and two-factor interactions. So we have to use a design that will correctly estimate all of those effects. And finally, a concept that we don't talk about very often, although there is a webinar specifically on this concept, robustness or ruggedness testing. This is where you confirm that a system is stable or has no effects over a very limited factor range. The FDA will require this be done for those of you who are in the pharmaceutical industry or in the food industry, anywhere where the FDA has some control over matters. They want you to do some robustness or ruggedness testing at the end of your process to confirm that over a small range of factor settings, there are no effects that are going to negatively impact the quality of the product. So you want to use a design with a small number of runs and yet still meets power requirements. We're not going to talk about what power requirements means. That is available in other webinars. But you do have to confirm power and then use a small design. Okay, so let's go into creating a fractional factorial design. We're going to start with a very, very simple design. This is a typical 3-factor DOE, and I see people using these all the time, so it's probably something that's fairly familiar to you. Usually when you look at your run chart, it's going to be randomized, and randomized is best. But for the process of talking about aliasing, we're going to keep our chart, our matrix, in standard order, which means that there is a specific pattern here, because then we can talk about how we use these patterns under the covers in how the software is doing calculations. So if we look at this 3-factor design, factor A starts with the low value, goes low, high, low, high, low, high, until we get done with the 8 runs. B has 2 lows, 2 highs, 2 lows, 2 highs, and C has 4 low values and 4 high values. So each column of pluses and minuses is unique. There are no 2 columns alike. When we calculate the effect of a factor, effect of a term, what we do is we find all the runs where that term is positive. So let's use factor C, it's easy to look at. So we have the 4 runs where factor C is positive. We look at the results for those 4 runs. So here's the 4 results, 81, 77, 42, 32. And we take the average of those results. So that would be the first number. Then we find the average of the results where C is negative. So we average these, find that average, and then the effect is the difference between those 2 averages. So our effect is the change in the response when we go from the high level of C to the low level of C. Okay. For factor B, the effect of B is the average response when we compare the high level of B, so the 4 runs where B is high, versus the average where the 4 runs of B where B is set low. Okay, and so those are, because the columns of pluses and minuses are different, all the effect calculations are going to be unique. Okay, now this is only 3 effects. In 8 runs, you have 7 effects to calculate. So here's the remaining effects. You have the 2-factor interactions, AB, AC, BC, and you have a 3-factor interaction, ABC. So likewise, you do the same thing, the same type of math calculations to calculate all of those interaction effects. You'll notice we've added 1 more column onto here. This is the I column, and it's column of all pluses. This represents the overall average. It is the more statistical term for this column is the identity column, or it could be an intercept, but identity is the statistical word for it. Looking through these columns, you can see that even the interaction columns are all unique. They all have a unique pattern. And so they're going to have unique calculations of the effect, and the I column is the overall average. Now, we're going to take this 8-run design and turn it into a half fraction design. What we do is we eliminate the negative ABC rows. That'll give us a half fraction. And to be honest, it doesn't matter if you eliminate the negatives or the positives, but the traditional method is to eliminate the negatives. So boom, they're gone. So we've lost half the data, because we're doing a half fraction design. Now, if you look carefully at this, and I've color-coded things to help you find these, you will now find sets of columns that are identical. So if you look at the A column, we've got a plus, minus, minus, plus, and you look at the BC column, plus, minus, minus, plus, those two columns are identical. They're exactly the same. That means we call these two columns aliases of each other. That's the word that's used. A and B are aliased together. They are identical columns. Okay, if they're identical columns, then what happens when we calculate the effect? Well, you got to average the pluses and average the minuses. The effect of A is minus 22.5. And the effect of BC is also going to be minus 22.5. We don't have two independent columns. We only have one column with two names. So A and BC are simply two names for the same math calculation. That's what an alias is, multiple names for the same calculation. Okay, now if you look at B, B is aliased with the AC interaction, and C is aliased with the AB interaction. So they are identical. We can no longer estimate 7 effects. We can only estimate 3 effects because you have 4 runs. So 4 minus 1, you have 3 degrees of freedom and 3 effects that can be independently estimated. All right, in software, we write this out in this manner. So let me talk you through some of this stuff. The I column equals the ABC column. I didn't show that, so here. I, all pluses. ABC is all pluses. So I equals ABC. This is called the defining contrast. And this is stuff you don't have to know, but you came here because you wanted to learn something. So a little bit of extra words to learn. The defining contrast defines the alias structure. So in a journal article, if you write the defining contrast, that defines the whole alias structure. And so that's really, an acceptable way of describing a fractional factorial design. Okay, so what we call the intercept is actually the intercept and the ABC interaction. Then if we look at this and we pull A out of here, so if you just take this we call this a 3-letter word. If you pull A out, what's left? BC. And so A is aliased with the BC interaction. If you pull B out of here, what's left? Well, AC. And if you pull C out, what's left is the AB interaction. So that is why this is called the defining contrast, because you can pick it apart and figure out what things are aliased with each other. A is aliased with BC, B with AC, and C with AB. All right, now another word. The word is resolution. And resolution is like the quality of the design. And higher resolution, higher quality is better. Resolution is determined by counting the letters in the shortest word in that defining contrast. Okay, so this is our word. 1, 2, 3. This is 3 letters. That means this is a resolution 3 design. Now, resolution 3 designs are color-coded red. What does red imply to you? Usually when we see the color red, we think stop, danger, fire, you know, these types of things. It's a very strong warning to us. And so the warning statistically for a resolution 3 red design is that main effects are aliased or confused with two-factor interactions. And we call a two-factor interaction, that's called a 2FI. That is shorthand that we use in the software and sometimes in our webinars. Okay. Now, if you've done a little bit of designed experiments, you'll know that the most common type of effects that exist are main effects. That's the number one thing we look for. The next most common effects are probably two-factor interactions. So running a design that confuses or aliases the main effects with the two-factor interactions is a pretty scary type of design. You are not going to get good information out of this. Let me show you math-wise what is going to happen here. Okay, so what I have done is I have taken the effects from that 8-run design. So we'll call those our true effects, you know, the actual real effects. And then I've also calculated the effects for the half fraction. And I wanted to show you how the math works here. So in the half fraction design, you can see that the A effect, what's called A, ends up being a minus 22.5. Where does that come from? Well, the real effect of A was a -1 in the full 8-run design, and the real effect of BC was a minus 21.5. So when we alias those with each other, we take the columns and they are added to each other. So you have a -1 and a minus 21.5 combined together. The total effect is minus 22.5. Aliased effects are linear combinations of the true but generally unknown effects. So it's the linear combination of them. It's not one or the other. It is the combined effect of everything that's aliased together. When we look at the B effect, it's B, the true B plus the true AC, so that's minus 20.5 and a -6 combined, they're a minus 26.5. So in a resolution 3 design, a red design, main effects are now biased by any existing two-factor interactions. So, you know, this is not a good situation to be in. We want main effects to be not biased by two-factor interactions. So that's why this is a red design, and we generally don't recommend using these for screening designs. Okay, let's move the conversation forward. This is a bigger design. This is a 16-run design. And this is the full factorial. So it has 4 factors, A, B, C, D, and a whole bunch of two-factor interactions and 3-factor interactions and a 4-factor interaction. With the full factorial design, there are no aliases. So you can estimate all effects. Let's say we want to make this into a half fraction. So we're going to throw away all the runs where A, B, C, D is negative. That means the I column equals the A, B, C, D column. So that's going to be the defining contrast. Now, column A in red here is going to be identical to B, C, D, also in red. And if you look down at the bottom at the effects, They're both 19. Calculation is the same. B is aliased with ACD, and you can kind of find your pairs working your way in until you get to AD and BC are identical. So you have a reduced set of unique columns, and these create the aliases. Okay, so how do we write this out? We write this out starting with our defining contrast, ABCDE, or sorry, ABCD, and then we can pull out A, and what's remaining is BCD. And then if we pull out B, what's remaining is ACD, etc. So when you pull out any main effect, you're always left with a three-factor interaction. Now, this is kind of cool because we make an assumption when we're using fractional factorial designs that three-factor interaction terms and higher have negligible effects. That is a key assumption to be able to use fractional factorials, that three-factor interactions have negligible effects. So we just zero those out. Assume they're not at all important, especially when comparing them to main effects. So this type of design is resolution 4, because we have 1, 2, 3, 4 letters. So it's a resolution 4. It is color-coded yellow. Now, yellow is a little bit better than red. It's more as a gentle warning, maybe slow down a little bit. But in fractional factorials, what it indicates is that you can get main effects unbiased from two-factor interactions. So that's cool, that's good. Now, the problem here is that we still have two-factor interactions confused or aliased with other two-factor interactions. Okay, so it's going to be labeled AB, but it's actually going to be AB and CD combined together. Can't separate those because it's one column. It's only one math calculation. Can't separate them. Okay, so these are the labels, AB, AC, AD, but behind the covers, under the covers, are more interactions. So a resolution 4 yellow design, we're going to estimate main effects well, but the two-factor interaction terms are aliased with each other. Okay. If we go up to a green design, resolution 5 design, then green means go. So you got to be thinking, okay, this should be a good design, and it is. Your main effects are aliased with 4-factor interactions, so I've shown these here. And 2-factor interactions are aliased with 3-factor interactions. So look, assuming again that 3-factor interactions are negligible, a green design can properly estimate both main effects and 2-factor interactions, meaning this would be a good design for characterization of a process. We would get all the information we need in a smaller number of runs than our full factorial design. Okay, so Design Expert has a selection matrix that is color-coded. The white designs are full factorials. There's no resolution with them because you can estimate all possible effects. The green designs are resolution 5 or better. So this one says resolution 5. This is resolution 6, resolution 7. So the resolution 5 designs or even better designs. So you can definitely get main effects and 2-factor interactions out of those. So green means go. Yellow, these are all resolution 4 designs. You will get main effects, but your 2-factor interactions will be aliased with each other. And then the red designs are all resolution 3. You can see that these are small number of runs, 8 run designs, maybe 16 run designs with a lot of factors in them. These will all have your main effects aliased with two-factor interactions. Why would you ever use one of those? I'm going to go back to that last design type, which was a design for a robustness study or ruggedness testing of your system, where the goal is actually to demonstrate, you can't really prove it, but demonstrate with a small number of runs that there is nothing significant in the process. So you would set up a red design, you would check power. You have to make sure that the design has enough runs to detect the change in the response that you're interested in. So if it passes the power test, then this design, the ideal thing is that the half normal plot where you choose effects would have all the points on a straight line, and there would be nothing jumping off the line, nothing significant. And again, if you want to learn more about those ruggedness tests and how to use those designs, there is a webinar saved on our YouTube channel on that topic. So you can go and look that up. Okay, I'm going to do a little demonstration here in Design Expert. Okay, so here is our screen. I just want to go down. I'm going to use this 7-factor column to look at this. So I'm going to first click on 7 factors and 8 runs, the red design. And when you click next, you get the alias strings. So you can see right here that your main effects are all confused with 2-factor interactions. So not a good situation. So I'm going to click back and we'll make this a little bit bigger. We'll go to 16 runs. This is a yellow design. So here, main effects are aliased with 3-factor interactions. And there's strings of them, but I don't care about that. I just care that these are all 3-factor interactions, and I am working on the assumption that those are negligible, so I'm not going to worry about those. Now, my 2-factor interactions, they all have strings, and so I could accept the fact that if I ran this 16-run design with 7 factors, I'm going to find my main effects correctly, and if I get an interaction that pops out as significant, it might be called the AD interaction, but it may not be AD. It might be CG or EF, or it could be a combination of these. So you have to be cautious with that. Sometimes you can use subject matter knowledge and which main effects come out as significant to kind of figure out your best guess as to which one it is. That's not proven with the math here, but sometimes there's enough information you can take some reasonable scientific guesses. Okay, if I go back and go down to 32 runs, that is going to be 16 more runs, so we can estimate 16 more effects. So that means we're going to get a lot more information. So now we can estimate a total of 31 terms, which brings us all the way down. Main effects and 2-factor interactions are good all the way down to the bottom. And at the bottom of the list, there's a little set of 2-factor interactions that are kind of tangled up with each other. They're not unique, but you know, again, when you do the analysis, if you see something that's one of these three come out as important, you might be able to figure out from subject matter knowledge what it is. We provide this information right before the screen where you name all your factors. So you might position factors that you know are unlikely to interact with each other in D, E, F, and G. You know, make the more likely to interact factors, put them in the A, B, and C letters. Okay, if we go down one more, now we're at 64 runs, which is a lot of runs. But it's a green design, and so we're definitely going to get all main effects and all two-factor interactions. And in fact, this is such a good green design with 64 runs that we're actually going to get all of our three-factor interactions. Okay, some of you are probably sitting out there and saying, I am never going to do 64 runs. That's just crazy. You know, that's way too many to do. So you're going to be interested in the next topic. The next topic, we're going to look at these minimum run characterize and minimum run screening designs. So just to give you a little preview here, minimum run characterize for that same 7 factors rather than 64 runs, we could actually get a resolution 5 design in 30 runs. Wow, cool. Or a screening design for 7 factors would be 64 runs. That's actually the same as here. But I kind of purposely jumped a little bit ahead. So let me get back to the slides here. All right, so as I just showed you, regular fractions of these two-level designs often contain more runs than are necessary to estimate the coefficients in the two-factor interaction model. And as I just showed, the smallest resolution 5 design, the green design for 7 factors, is 64 runs, but there's only 29 coefficients to estimate. So we have a balanced minimum run design for 7 factors with only 30 runs, saving you more than 50%. So that's pretty cool. Now, there's always disadvantages. And disadvantage of minimum run designs is something called partial aliasing. So I'm going to show you what that looks like in an example. But these designs are irregular fraction designs. Because of this partial aliasing, effect estimates are dependent on the other terms that are chosen in the model. So choosing the terms is not as clean as you're used to. But Design Expert has very powerful algorithms built in. And so if you just watch as you're choosing effects and do it carefully, then it works out really well. A few examples, and this is one of my favorites, 6 factors. The regular fractional design is 32 runs, but there is a resolution 5 minimum run design that's only 22 runs. So that is a 1/3 savings. Very, very nice. I showed you the 30 run design, but you can see, you know, for more factors that these designs offer some really nice savings. Okay, so I'm going to show you building a design like this in Design Expert. So I'm going to take a design and I'm actually going to rebuild it. All right, so this is an 8 factor design. If we had looked at the regular 2-level options for 8 factors, if we wanted to be able to estimate all main effects and all 2-factor interactions, then we would have probably gone with this 64-run design. But we know that's a lot of runs. So if we wanted to save runs, the natural inclination is to go down here to 32 runs or even to 16 runs. Yes, that saves you resources, but you're only getting main effects, nothing else. So what else can we do? Well, look at minimum run characterize. 8 factors. Rather than doing 64 runs to get all main effects and all 2-factor interactions, we can do 38 runs. That is the minimum number of runs required to estimate main effects and 2-factor interactions. You can't do any fewer and get this information. Okay, now I'm going to warn you, the next screen I'm going to show is scary. It is what partial aliasing looks like. You don't normally really have to look at this. All you have to do is know that this is a resolution 5 design built for characterization, and thus I promise you it's going to estimate both main effects and 2-factor interactions. But here we go. So this is what partial aliasing looks like. So A is aliased with 1/3, 0.3, 1/3 of the ABC effect and 1/3 of the ABD effect and 0.03 of the ABE effect, etc. So you can see that there's small fractions of 3-factor interaction terms. Well, what is the assumption for 3-factor interactions? We assume that they're negligible. So a little tiny bit of a negligible effect is nothing. So we can just cancel all of those out. So all main effects are aliased with 3-factor interaction terms. And I'm going to scroll down to a 2-factor interaction to show you this. And you can see it's the same thing. We are partially aliased with 3-factor interactions, which we assume are negligible. So that means that this type of design meets the basic definition of resolution 5 in that we can estimate main effects and 2-factor interactions free and clear of any other main effects or 2-factor interactions. Okay, so I'm going to reopen that design with the data filled in. So this is that 38-run design. And just to show you the half normal plot. Oh, and when you click on Start Analysis, it will always, with these irregular fraction designs, these minimum run designs, it will always give you a note. The design is not orthogonal. Here's the important part. The coefficients change depending on the other model terms. So click OK, I know this. And so it's really important that you click on these one at a time. I'm always going to start with the biggest one, the one over to the right. I'm going to click on it. And did you see things move? I'm going to deselect it, show you again. Okay, so when I click on this, I put it in the model. That changes the calculations for everything else. So you have to pay attention. So I click on it. Then I click on the next one. That pulls it out. If it pulls it out, that's good. It means it's a strong effect. If it pulls it into the line, then that means it's not an important effect. So things kind of shift around as we're clicking on these, but we get them all selected, and these are kind of the final effect calculations, and then we would build the model based on this. Oh, I'd say yes to hierarchy. Yeah, so I get everything in the model, say yes to hierarchy. and you proceed. I'm not going to go through any more of the analysis because that's shown in other webinars. So my purpose here was simply to show you that with the minimum run designs, the effects change a little bit as you select them. As long as after you click on them, they are significant, then that's good. If you click on a term and it goes back into the line, then you remove that term and just let it sit. You don't want anything that's not significant to be in your model. Okay. All right, so now we're going to talk about screening. So the concept of screening is to discover the few primary factors that drive the process. We assume that interactions might exist in the system. So a minimum run screening design is for absolute minimum run screening. Often gives you some nice savings. They require 2 runs for each factor. So if you have 5 factors, 5 times 2 would be 10 runs. However, the problem with absolute minimum run is that if you lose 1 run, even 1 run, then you lose the entire design. That design will become resolution 3, and the main effects become really badly aliased. Besides the fact that you could lose power also. So the default of Design Expert is a minimum run plus 2 design. So we have added 2 extra runs as a safekeeping, a robustness for you, so that if you lose a run, you don't lose your whole design. Because, you know, when we're doing experiments, there are mistakes get made. I know this. So we are kind of trying to protect you a little bit against that and just pad the design just a little bit. Okay, so that is the default. You can override it if you have to, but if you have to override it, then you have to make absolutely certain that you can get every single run without losing any. So one nice design would be the 5 factors in 12 runs. Now there's 6 factors in 14 runs. When you get to 7 and 8 factors, the regular designs are 16 runs, so there's not really a benefit of going to the minimum run design because those regular fractions are already the minimum runs for 7 and 8 factors. But once you get to 9 and 10 factors, then you get a great savings again in the number of runs that you need. Okay, so I have time to show you one example of this. Okay, again, I'm going to rebuild this so you can see it from the start. All right, so this is a 9-factor design. So what was our original choice for 9 factors? Now we're talking about screening here. So we're interested in a yellow design. So perhaps this 32 run design. If you want fewer than that, then you're into this red design. It's not a good choice because your main effects are going to be confused, aliased with interaction. So if any interaction is in the system, it will get combined with the main effect, and that main effect will not be correct. That information will not be correct. It would be very misleading. So 9 factors screening design is 20 runs. Notice that this is checked minimum runs plus 2. Here's the option, just minimum runs. That would make it, change it to 18. We say warning, don't do that. So we prefer the minimum run plus 2. Here again is a partial aliasing. Main effects are good. They're just aliased with 3-factor interactions. But once you get down to the 2-factor interactions, you can see that they are partially aliased with each other. Okay, but this would be a successful design in figuring out our 2-factor interactions. So again, let me open this up with some data in it. And we'll just look at the analysis. We get the orthogonality message again, reminding us to just click one thing at a time. And we click on this factor. This is actually the big factor. I would contend that that line goes straight through all of those. You can see on the Pareto chart that they are all underneath this line. We were actually, this particular experiment was actually a robustness study where we were trying to prove that nothing was significant. Unfortunately, there is something significant, the reagent that they were using. And so this fails actually the test for robustness, but we did find out that factor A was a big effect. So they can go back to the process and work on that factor and try to reduce its effectiveness. All right, so let's recap here. And when you're choosing a design, it comes down to a few things. Number one, what type of information do you want to get? Number two, how many factors do you have? And number three, what is your budget in terms of how many runs can you afford? So if you're wanting to get just main effects, just those linear effects, then you want to use a design that keeps the main effects information unbiased from 2-factor interactions. So you're going to use a yellow resolution 4 design, or you can definitely use a resolution 5 green design. That's fine. You do not want to use the red resolution 3 designs, and that also includes Plackett Berman or Taguchi designs, which are also resolution 3 designs. For characterization, finding main effects and 2-factor interactions, then you need to use a design that can estimate all of those. So a full factorial white design or a green design, again, resolution 5 or higher design. Robustness, ruggedness testing. Use a design with a small number of runs, yet still meets power requirements. This is either resolution 3 if the power is sufficient, or resolution 4 if you simply need more runs in order to get the power. Okay, so a question came in, and I didn't put this in here, but a question came in asking if, how do the definitive screening designs fit into this? And the question was specifically, are they like the minimum run Res 4 designs? And no, they aren't. Let me show you where you can find them. I'm going to just do a new design. Oh, no. Okay, so underneath response surface is another type of screening design used very specifically for screening. It is a design that has 3 levels. It has a low and a high and a mid-level, a 0 level. So if I just build it for 4 factors, I've got the low and the high. It's going to be 13 runs. Notice this is under response surface because of that 0 level, it actually needs the analysis tools that are in response surface designs in order to analyze this correctly. So we put it in a different area. So this is going to give you more than just -1s and +1s. You can see that it gives you zeros in here, mid-levels. And this design, as it was created, is great for screening, meaning it can correctly estimate main effects. What it can also do is it can give you an aliased view of second order terms. But those second order terms are combined quadratic and 2-factor interaction terms. So I'm going to show you the aliasing pattern for this, just kind of an aside here, under evaluation. And what I have to do is I have to add in all of these terms. So I'm going to show you the aliasing for a quadratic model, which would include both interactions and quadratic terms. And go to the aliases, and you can see main effects, perfect, great screening design. But then when you get to the second order terms, they are confused, they are aliased with each other and with quadratic effects. So yeah, again, definitive screening definitely can be used for screening, but things that are higher order, they are all aliased together. So it is similar to an MR4 design, but it's just built on a slightly different basis. Good question. All right, so similar guide here. We want to, if we're doing screening, we want unbiased estimates of the main effects. So the algebraic fractions are great. The minimum run screening designs are great. And gosh, right in here, definitive screening design. So I had left it on the slide. And then for characterization, when we want estimates of both main effects and 2-factor interactions, full factorials are great, or resolution 5, the green designs that are regular fractions, or the minimum run characterized designs. Note, on both screening designs and characterization designs, if you need to increase the power of a fractional factorial design, don't replicate. Instead, go up to a bigger design, add a new fraction, because that additional fraction is going to increase power. It's also going to reduce aliasing. You'll be able to estimate more terms, and it adds new process combinations that better fill your DOE space. So you are testing in more areas of the design space. All right, so that concludes our discussion of fractional factorial designs. I've mentioned a couple times our YouTube channel, very excellent resource. If you really want to get a better education, keep increasing your education, you can also consider coming to our workshops. Our Modern DOE for Process Optimization workshop focuses on the factorial designs, fractional factorial designs, and response surface designs. And our mixture design workshop focuses on formulation studies. There are screening designs for mixtures also. These are offered publicly, they are offered privately to companies, and if you are an international person outside the US, and you want to take it on your own time, we are now offering these asynchronously. So you can purchase the class and do it within a specific time period, and we'll still be there to help answer your questions. All right, so I would like to thank you for listening today. I hope you have learned something about fractional factorials, and I hope you will find that very useful.